If we can harness the power of quantum information sciences and build the next generation quantum computers, or the next generation quantum sensors, or the next generation quantum networks, we definitely drastically are going to change the way we see our world. My name is Bert de Jong. I'm a senior scientist at Berkeley Lab. I'm a computational chemist. I use big computers to solve real scientific problems in batteries and so on. And the problem is that classical computers cannot scale to infinitely. We are running out of resources and energy to run classical computers. So I started to think about what are alternative computing technologies for me to use, and that ended up being quantum computers. When it comes to quantum information sciences, it's a really new, revolutionary area. We already deal with the influence of quantum mechanics in everyday life. Our lights, our batteries, our electronics, they're all driven by quantum mechanics. So in classical computing, you have bits. You have zeros and ones, and it's either a zero or a one. What's the difference between quantum computing is it can be a number anywhere between 0 and 1. Most of our simulations of the science problems that we have in chemistry, materials, or in physics are done on classical computers. We know from the science problems that we really want to solve that we would need a classical computer that is many orders of magnitude larger. The potential for quantum computing is actually to do this in a way more efficient way. The first things I would do when I have a quantum computer, like I would have a classical computer, is start to think about how we can run algorithms on that, how we can run simulations on there. So my team is primarily focused on developing the next generation algorithms, find ways to deal with the noise that the quantum computers have, and then find ways to actually do real simulations. We now are entering an environment where we have up to a couple of hundred qubits, and people are probing approaches towards 1,000 qubits, but they are very noisy. And actually getting rid of the noise will be almost an impossibility. Why? If we want to have perfect qubits, we have to do it better than nature can. And that's never going to happen. The research at Berkeley Lab is really focused on building less noisy quantum computers so that we can do more accurate simulations, building better quantum sensors so that we can actually probe the fundamentals of nature, and building the next generation networks so that we can move information in a secure way. We are now starting to think on how we could do new types of algorithms using quantum information technology itself. And so we can actually ask and answer different, even more important problems, not just what is the ground state of a molecule. No. What is the dynamics of that molecule, which is critical to understand chemical reactions that drive, for example, catalysis or drive the conversion of biofuels. Now I lead a team that is about 450 people across 15 different institutions that do the hardware development. So I see up close the challenges that they have to deal with, try to understand where the challenges are, and then figure out if there is a way for co-design between the hardware and the algorithms teams to really advance the technology, and then being able to do real science problems with these quantum computers in the near future. This is a research effort that needs everybody. It's not just the physicists, it's not just the chemists. It requires computer scientists, applied mathematicians, material scientists, physicists, engineers. And so from a society point of view, if we can build better materials, engineer better systems that we need in everyday life, then it will advance our society.